Well, good morning. I'd like to introduce Dr. or Professor Mauricio Santillana. We've known each other for a very long time. We were both graduate students at UT Austin, which is a very interdisciplinary place. It brings together mathematicians, physicists, engineers. I was an engineer, and Dr. Santillana was a mathematician, or is a mathematician, should I say. But it was a wonderful community to meet people from other disciplines and also learn from them, and we've been friends ever since. So I'm very happy that he accepted our invitation to give a presentation. What I'm going to say about him is we'll highlight that he's definitely a very interdisciplinary person because he's a professor in both physics and electrical and computer engineering at Northeastern. That's very recent, this appointment. And he's an adjunct professor at the Department of Epidemiology at the Harvard School of Public Health. And in addition, he's director of Machine Intelligence Group for the Betterment of Health and Environment, cutely called MIGHTY, at the Network Science Institute at Northeastern. So, thank you very much. We're very willing to hear what you have to say.
Thank you.
Thank you.
And so, could everyone here is from mechanical engineering?
Yeah.
Yes. Okay. Very good. So, in my scientific career, I have worked in many research fields, and some of them were more, embedded in an engineering environment. But as Albert said, my PhD is in mathematics. My undergraduate is in physics, so I'm a physicist, I guess, as well. And so I have done work where the goal was to solve differential equations or models that were designed to capture the dynamics of something, some phenomenon out there, like atmospheric chemistry in the atmosphere, or water flow due to hurricanes, or where people would settle in general, like population growth patterns. And this was with an emphasis on giving access to those people to water. And then later I became a professor in medicine in a hospital at Harvard. And so I did a lot of work. I just realized there's a typo here. But the whole goal there was to monitor how a patient was doing and then determining at what point one needed to change care. So it was a lot of signal processing and then basically identifying anomalies and then thinking, well, this care plan is working or not, and we may need to change strategies. So today I'm going to be talking to you about epidemiology. And I will describe it to you in a very broad sense. I do have some keywords on my slides for those of you who are interested in the mathematical or the algorithmic side of things. And you can ask me anything. So we can make this, given that the audience is small enough, we could make it very interactive. So if you have questions, you can interrupt me any second. And I'm happy to. I don't have an agenda. In fact, I would love to just chat with you guys. And so I'll give us an excuse to talk about things. And so what I will be telling you about has involved a lot of people. So I'm putting some of their pictures there so to acknowledge that they have contributed to some of the things that you're going to be seeing. And then these are a collection of collaborators. And because there's some students in the room, I thought it would make sense to throw in some terms of the techniques that we use. Because these techniques, while they may be from applied math or statistics or from the machine learning side of things, they are widely used across engineering fields. And so maybe some of you are familiar with some of these keywords. And so let's get into it, right? So the work, the reason why I was interested to get into epidemiology in the first place was because I became interested in the fact that companies, when we click agree in our phones to everything, right? We just want to play with the phone, right? And so you're like, I want that game, and then you say, agree, agree, like, yeah, whatever, right? Like, I just want to. So what we frequently are not fully aware of is that we are agreeing. So this is what if you have an iPhone, this is how you unlock your iPhone, right? You look at it, and it's magical, so you're like, that's great. And then, this is how people monitor who's walking where. And so, say, imagine Facebook or TikTok or Instagram or any of these, or LinkedIn. So there's something in the back end that tells them who you're connected with in some sense, right? So interestingly, in the context of, I realize that you can see biosurveillance at the very top. So a cute way to see this is rather than understanding that these companies are using all this information to sell you things, and because most of them, it's free, then we are the product, as you may know, right? If you don't know, then now you know. So that's why it's free, but because they're selling us, right, or whatever we do. But a cute way to look at it is to think that, well, one could do biosurveillance. Namely, we could monitor what people are doing and perhaps use that as a thermometer for what's happening in our societies. And as I said, these big companies use them for predictive analytics to learn what you're going to buy next, or where you may want to go in the next, like next weekend, and when you're there, they'll advertise things that you can buy, right? And our aspiration is to go from that same kind of data ecosystem and similar techniques to the ones they use to sell you, like to build recommender systems, for example, but to help medicine and public health. So we, unfortunately, we're not Google, we're not Meta, we're not Amazon, so we cannot benefit from you guys. But the question is, could we use some of the data that these companies are collecting for better purposes from the perspective of healthcare? And so, what kind of a problem is one interested in epidemiology? And so, what I'm showing you here is a collection of curves. You see them in gray, and these curves represent the number of people with influenza-like illnesses in the U.S. over the past, say, 20 years, I think. And what this is showing you is that in different years, there were different times when influenza hit our population, and some, a lot more people were sick, some other times they weren't. And so what's interesting about this data is that the US has collected information on influenza-like illnesses for about 20 or 30 years. So it's a good data set to learn, right? But a lot of people know the x-axis is time, and the numbers show you what people call the epidemic week. So epidemic week 52 is typically at the very end of the year. So they start counting in January 1 to 52. And so this is kind of December 31st, somewhere here. And you see that there are epidemic outbreaks on either side. And so, interestingly, when you go pay somewhere with a credit card and you don't have enough money to pay, or say with your debit card, your card is denied immediately, right? So they know. So there's a way for us to have a very updated data system that tells when you run out of money. Sadly, for epidemiology, if you ask how many people are experiencing a fever today in a hospital or anywhere in the US, if you look at the data that's available, it's always about a week or two old. So it takes forever. So it's not like the banking system, or it's not like your email, where like you see the most recent email like sent 3 seconds ago, right? So the technology exists, but it's not available for public health purposes, which is sad. Which means that if you were to ask me how many people are sick right now with a given disease, so suppose this is the real time, suppose this is right now, we only know what happened a couple of weeks ago, right? So the exercise of what we call nowcasting is already a forecasting exercise from the perspective of the data availability. So that's one open problem to tell a decision maker, these are the number of people who are sick right now. And then, of course, they want to know, well, is it going to get worse or, or is it going to get better, right? And we all experience COVID-19. And so now you know that, we understand that if cases are going down and deaths, and so people feel like, okay, we can relax and, no need to panic about going to the movies or whatever, right? Even though you may get sick. Um, but so knowing what may happen in the short term is important. And then, epidemiologists get ambitious and they say, well, I really want to know how many people are going to be affected, when the peak is going to be reached, and how long this outbreak is going to be, right? And so typically, if you wanted to build models and understand the dynamics of these outbreaks, you would need to observe many, and then you can create models that capture some of the dynamics of these uh, um, events. When you have an emerging outbreak like COVID, then that gets challenging, and then we'll explore that. And then from a modeling perspective, you can think about doing this exercise of forecasting or nowcasting um, at different spatial resolutions, right? So you could do this at the national level and wonder if that's useful for anyone, or you could do this at the state level or city level or hospital level if you want, right? And so, now let me just say a philosophical statement here that that comes up frequently with people that. Has anyone seen this plot before? So this plot shows you in the x-axis time. It goes from 1955 to 2015. And the y-axis is the accuracy that we have in weather forecasting. The two lines, this is the accuracy we have. Think about predicting the temperature, tomorrow. This is the 36-hour ahead forecast versus a 72-hour forecast. So that's like 3 days, I think. So what this says is that over the years, we have gotten better, right? And in fact, if we were all the way to 2020, maybe, the closer we are to 100, the better, because that would mean that we're always right, right? So the interesting fact about epidemiological forecasting, and this is similar to predicting the economy, is that if I were to tell you that there was a bad disease, respiratory disease, that if you get sick, or if your parents get infected or something, they may die. Then in principle, if you trusted me and you thought, this guy is saying something that will occur, then you would react to that. And you would recommend your parents or yourself or your neighbors, let's do something about this so that we minimize the outcomes. And what that would mean is that if I have a prediction of what's going to happen in the next 3 weeks, for example, and I tell you that, right, and you react to that as a society, then my predictions in principle will be wrong because I perturb the system and there's a feedback mechanism, right? The feedback is not so clear for weather, right? Because even if we know that there's going to be a hurricane, or I guess in South Dakota, there will be a fire, let's say. I saw this morning that there was a hazard of fire. Almost anything you do, I mean, you can build things that lower the risk, but in principle, if there's a fire, it's just either going to happen or not. Does that make sense? Good. So now, a lot of people who are using mathematics and differential equations use equations like this. They're nonlinear, and maybe at this point, some of you have heard of these models. They're called the SIR models, susceptible, infected, recovered models, and people make them more complicated. And I may get to talk about this, but I'm going to focus on something else, which is the way in which I got hooked into doing this kind of work. And then we'll explore what happened during COVID-19. And then we'll see some more of the math if we have time. Okay? And so, as I was saying, those curves I presented to you are, keeping track of who got sick with something that was respiratory, looked like an influenza-like illnesses, And so since there have been so many efforts deployed to monitor that, uh, back in the days, I think around 2008, I started paying attention to this, and there was an effort to go from what the way I started at the top, right? From this data, the data that the way you search, the way you post online, the way you interact with your friends, to map that social media conversation onto something that would look like a curve that describes this dynamical system, which is how many people are sick with one, um, say, with influenza. And the hope was that because our systems, our data systems are so delayed, then in principle these signals could bring us up to this nowcasting, right? And so you can think of them as thermometers, right? Like if fewer people are going to the movies, or there are more cancellations in restaurants, or for example, there are a lot of reviews that are complaining about the fact that the candles that they bought were supposed to be scented, but they were not, right? All of these are true things that happen. In fact, this was during COVID, because anosmia is one of the symptoms of COVID. Then people were ordering candles, and they're like giving them really bad reviews because like it just doesn't smell like anything. So they couldn't smell. It's not that the candles didn't smell right. So the hope is to map those things into something that looks like this, which is, so these are actually forecasts of what we thought was going to happen in real time. So these are weeks, this is time, and this is, again, the y-axis is think of what percent of the population was experiencing an influenza-like illness. And so what you see here in black is what was observed according to the Centers for Disease Control, and the red, which has a cone of uncertainty, are predictions that are being updated every week. And so anytime the black line falls within those confidence intervals, we feel like we did a good job, right? So I want to tell you how we do that, because we do that every single week. We communicate with the Centers for Disease Control. We tell them this is the number of people we think are sick. Lately, we have been communicating with them how many people we think will be hospitalized, right? And so, so the long story short is we use multiple social thermometers to assess what's happening, and then we translate those thermometers that come from Google searches, from the way people tweet. Now it's X. I don't know what the verb for tweeting is anymore. Or what clinicians are searching for whenever you go see a medical doctor. And then I'll try to convince you that these techniques that I will present to you are transferable, so that you can predict outbreaks of other diseases, outside of influenza, and even in emerging infectious diseases like COVID. So this is how I got hooked into this. Google, at some point in time, how many of you have seen these Google flu trends, these three words together? No? Okay, very good. So it turns out that I think it was in 2009, according to that paper, Google published a paper where they said, look, if you monitor the number of people who are searching for influenza-related terms, you can know ahead of time how many people will show up in an emergency department. And so the plot looks like this. This is what the New York Times, so it was splashed in this paper, and it's very highly cited. And it was a revolutionary contribution technologically, because it was mapping what we are doing, namely how we're searching, how we're interacting with the search engine. It was mapping into potential useful information from the epidemiological perspective. And this is a plot that my team produced years after this was discontinued. But just to share with you, so if you look at these two signals, you have a red and a black. Black is the number of people who were sick with the flu in South Africa. And then red is the number of people that are searching for the word bronchitis, right? So if you look at that, of those two figures, those two curves, then you say, well, they kind of look similar, right? So in principle, one could find a mapping from the red to the black. And the crucial thing here to note is that the red is available about 2 weeks before the black. So it tells you roughly if things are getting better or worse, right? So that was the idea from Google. So they published their paper, and then very sadly, like 2 months after they started deploying this tool, so it became a tool. It was a website. You could go and check, how many people are sick with the flu. So this is the ground truth, whatever the CDC was estimating. And in 2009, I don't know if anyone remembers, but there was another pandemic. It was called the H1N1 pandemic. It started in Mexico and it hit many countries. It just wasn't as big as COVID-19, and the consequences of getting sick were not as bad as with COVID or Ebola or some other outbreaks. And so, but these technological tools that Google designed failed to capture that epidemic outbreak.
Mauricio, yeah. The red curve is actually measured data. This is not predicted. Okay.
Correct. And the blue was the effort from Google that was predicted. So in principle, it should be shifted forward, the blue.
Yeah.
So it didn't work. So people were really concerned. They said, well, this system, it was cool, but it seems to not work in real, real life. So, but then Google said, oh, yes, we found the errors. We're going to fix it. They started testing here, and then their system seemed to be good. So they were really happy. And then 2013 happened, and they had now an over prediction. They said about twice as many people would get sick, when really, so they predicted about 10% of the population would get sick in 2013, and really 6%, roughly, right? So they got the peak really bad. And so they made it into the journal Nature again, but this time without a good thing to say about them. And I have some colleagues who wrote a big paper showing that this system was flawed from the beginning. And the sad part is that a lot of news came during that time, and it was all really negative about this data and these techniques. And so everyone said, this Google search business, it was flashy, but it just didn't deliver. So, and it was then that I had a student like one of you guys in my linear algebra class. And the guy said, in our linear algebra class, we have a final project where you get to choose a data set and you get to solve something that you think would be cool. So my student decided to work on replicating the efforts of Google's flu trends. And he told me, what if we managed to fix it, right? Like, well, give it a try. So he downloaded data from Google, and we realized that the data that Google was willing to share was low quality. So the input variables were not very good. But if you implemented their algorithm, you kind of got a sense that he was going up at the right time and so on. So it was cute. So we thought, well, what if we managed to improve their algorithm with respect to this bad data, so we could say at least that we had something better. It would be a nice, cool final project for the class. So the long story short is that we did this, and to our surprise, we improved the algorithm, and I can explain to you what we did. But and then we produced retrospectively predictions for what our algorithm would have made in terms of predictions compared to what Google did historically. And just keep in mind that we didn't expect our predictions to be better because we had kind of bad data, right? But we showed that even with bad data, but with a good algorithm, you could produce predictions that were better or closer to what was happening, right? And we would have detected the H1N1 and so on, right? So we were excited, and so I told my students, since the first paper of Google had been published in Nature, I said, well, let's send this to Nature. So we sent it, and they like, whatever. For sure, your algorithm is wrong. Then we sent it to Science, and then, in this business of publishing, we started going down until we landed in this journal. That's a medical journal. We had 13 reviewers. So for those of you who are used to publishing papers, it's the paper that I have had more reviews in my career. 13, and then it took a year on the review, and then they said, well, we cannot find any problems, so I guess we'll publish it, right? So they published it, and then Then I got a call from Google, and they said, oh, your algorithm doesn't work. And so, but the, the guy who was calling me was the engineer coding it. So I said, could you tell me what your lines of code say? And so he started walking me, and I realized that one mistake he had was that there was a command that should be inside a for loop, and it was outside. So I said, oh, just change that inside the for loop. And he said, like, oh shit, actually works. So we were really happy, right? Because this started like as a class project, and then it was impacting uh, reality, and so and then we appeared on the news, right? So we had our 3 seconds of fame. My student was really happy about this, and then the good thing is that Google actually acknowledged. They said, in fact, yes, this algorithm is better than ours, so we will be implementing it, right? And so the long story short in terms of what we did that they had not done is that we had brought something that in engineering is called data assimilation, and that it happens very frequently in weather forecasting, which is you have sensors out there that are measuring, say, the wind speed, temperature, etc. And so you force your models to fit the most recently observed data, and then from there you produce your forecast to prevent what people call model drift in the short term. And just doing that, which is we call it dynamic training in this context. We we got this to work, and it was good to use our quantitative minds to improve something that felt like it was making progress. And then Google, because they had a lot more data, they asked me a lot of questions. They said, what if you had more access to all the data that we actually have access to? What else? How else would you improve this? So I talked to them for a while, and then they asked me to be a reviewer for a paper where they summarize all the things that I had told them, right? So, and because I was, and perhaps I'm still a little bit of a narcissist scientist, I wanted to either be invited to be a co-author, or at least that they had a statement somewhere acknowledging that this had emerged from our conversations. But instead, I said, look, I cannot conduct this review because I have a conflict of interest. It got published eventually, but instead I got revengeful. And I reached out to one of my colleagues in the statistics department at Harvard and said, I gave them all these hints, but they actually did it wrong. So I asked him, could you help me? Let's just write a good paper and prove them wrong. So it was very immature, if you will, but scientifically we were improving the field, so we wrote this paper. And we showed that that paper was suboptimal, and so we were happy that that we published that, and then I get another phone call from Google, and they said, you know what, you guys seem to be obsessed to prove us wrong, and we're just not going to do this anymore. So we're going to stop this whole thing, but we're happy to send you the data if you guys want to continue this effort. Then you take over, and just we're done. So they shared the data. I was at Boston Children's and Harvard at the time. And of course, there was a reaction in the news, and so they started offering us the data. And so we started, at the time, we started working very closely with the CDC, the Centers for Disease Control, and we started asking them, okay, what would be useful for you if we could provide predictions and forecasts? And at the time, we were also monitoring other data sources. For example, we had an agreement with a company that monitors the number of doctors searching for very specific terms in different points in time. So they have a time series of how many doctors are, say, looking for the word Tamiflu. I don't know if you've ever gotten the flu, or if you know people who have gotten the flu, and then in the first 48 hours, I think, or however many, if you take this antiviral, you may experience a milder infection. And so over time, if you look at how frequently doctors are searching for this, then you see that there's a really high correlation of people who are visiting the hospital due to a respiratory disease. And we were looking at other data streams like apps that keep asking you, are you feeling well this week? And if not, then what's wrong, right? And so maybe you have seen this, maybe not. But at the time, we showed that all these data sources could be used as input to produce models that could nowcast and forecast flu activity in a reasonable way. And so, let me see. And then I got a call now from the CDC, and they said, we see that you keep writing papers, that you can get fairly good predictions of flu. We would like you to send us your best model. We don't care that you have 5, just send us the best, right? But I don't know if, so I'm going to assume that some of you know what Netflix is. Okay, perfect. So at least you know Netflix. So Netflix, about, I think it was in 2010, that they were yet not an empire as big as they are now. And they moved all their operations from CDs, or DVDs, they were called back in the days. Some of you don't know what I'm talking about. But they were discs that contained the movies, right? They would ship them to your house. And about, I think it was 2009, 2010, they moved into, like now you just turn on your TV and it just appears magically, right? Because it's like you're browsing, like their web browser. So now that the movies are available, I mean, for the older ones, I know this sounds stupid what I'm saying, but I'm just saying this for the younger ones. So what happened is that Netflix created a system, a recommender system, that every time you as a user sit down in a different point in time, say in the afternoon or a Sunday versus a Monday night or whatever, it would recommend you what you want to see. And in principle, they want it to be accurate so that you would be hooked into the app. So they found out that there was no single model that could predict for every user, for every time period of the day, what the user wanted to see. Instead, they found that if they used an ensemble, then there was one model that was very good to predict what kids wanted to see on Sunday mornings. But there was another one that during weeknights and so on. So they stitched together this kind of Frankenstein model, and they called it an ensemble. That's what they use nowadays. So it's like most companies use ensemble models. So I thought at the time, well, why don't we use an ensemble model and see whether the predictions that we're getting with each of these 5 or 6 models would be improved in some way by creating like a machine learning algorithm that combines them all, right? Would that be a good idea? And so what you see here is in each row a different model. Think of them as different models, and each column tells you an accuracy metric. And maybe you just, this is an error metric, right? It's a root mean square error with respect to the signal. So what we discovered was that if we used all of the weak predictors, we call them now weak predictors because they are biased, right? Because if you're just staring at what people are tweeting or staring at only what people are searching for, they all have their own biases. But if you combine them all, in this specific experiment, we noticed that the correlation with the signal was much better, and there was an error reduction even with respect to the best one. So that meant that the model that we had to communicate with to the CDC was not the best performing model, but in fact a collection or a Frankenstein of all of them. Right? And so, so we started doing that, and that's what you see here. So this is that model, okay, that uses a lot of data sources. And so, let me see. I promised I would show you. So this is just a brief slide, or about how we map tweets that are relevant for infection. So these are kind of the input variables that we need to use natural language processing, for those of you who know what that means, because it's not feasible to stare at the pipe that's getting all the tweets in real time and check, no, this is a good tweet, this is not a good tweet, like you need to do this computation. So anyways, let me see, the time, 34. Yeah, so I'm gonna continue talking about this, because for those of you who are into machine learning, our team has also worked on using neural networks and very soon we'll try transformers. I don't know if you are into this whole craziness about transformers, but now that's the preferred technique. But I'm going to soon switch to. Uh, um, I promised I was going to tell you about other diseases, but I think I'm going to go directly to COVID to tell you what we did during COVID. But I'm going to pause and ask if you guys have questions so far. Yes.
Just a general question, in terms of like the users of this type of model and data, is it mostly like hospitals so they can predict their capacity levels, or higher up at CDC, like how are they actually using this prediction?
Yes, so the CDC, um, um, I'm going to give you the exact answer, even though it's not what we wanted. The CDC is an entity that is a federated entity, which means that they don't have any authority over each state. And that means that states do not have any, what's the word? There's no way to force any state to provide data to the CDC. That's the bottom line. Which means that the finest spatial resolution that the CDC can demand using their own kind of incentives is state level, right? So for a hospital, if they know that there's a lot of flu in your state, maybe for South Dakota, the strongest signals come from Rapid City, maybe, or maybe there's another city that's very highly populated. But if you are in, say, California or New York State, there are many cities, and so if you live in San Diego and then you hear, oh, flu levels are increasing or COVID, but maybe it's because it's in San Francisco, it's bad, but it's not bad here, then you shouldn't care, right? Because you should react only when there's something. So because of the implementation or the way the CDC works, we can only share state level predictions. We also work with Boston, the Public Health Commission in Boston, and some hospitals. So in principle, we do have partners that are looking at this to allocate resources. For example, how many doctors should I have in my emergency department this week? Should I ramp up? Should I open up beds and so on? So we have some partners where they are using them as we would like them to use them, but at the national level and state level, it's still not a reality. Does that make sense? Any more questions? Some may come, some more questions here. But COVID-19. So you all remember this, I suppose?
Vaguely.
Vaguely, right? And this is a slide that I prepared in April 2020. So at the time, the main theory was that the COVID had come from bats and another weird animal. And then maybe you guys have followed up, but now people, just so happens that Wuhan is a place where there is a biological lab where people study gain of function, which is a biological term for what if there's a virus like the flu, and what if we start making it more aggressive with humans? Could we come up with a vaccine? And so in China, they do this as a way to prepare themselves against bio threats. The US has these centers as well. And so, of course, there was this concern that maybe that this was a leak, that they had produced a virus and that, it got leaked, right? So, and of course, many people have many ideas about this. But I'm going to get to what happened, what we saw happened, and without the conspiracy theory behind. Not that the conspiracy may be wrong or right. It's important to keep finding the truth. So no complaints there, right? But so we had written multiple papers. So when COVID hit China, the Chinese government had 2 postdocs from China. The Chinese government reached out to us and they said, could you produce this thermometer, like forecasting things to see what's going to happen in China? And for us, we were in the US and we were thinking, oh, this is happening somewhere else. So yeah, we'll do that. We had all the capacity. China, as a country, they don't use Google, but they use something else called Baidu, which is it's their own version. And they shared also news alerts. They shared human mobility data as well. So we built these models. It took us a while. And so by February, we had this gray area is the time that we needed to train our models in a very restricted way. And then we tried them like, I think a week into the future. Sorry, the predictions were 7 days into the future, and then it was a moving prediction, right? Like I showed you with the other plot. And we showed that our models were good at predicting, except that the Chinese government had reacted very aggressively against the virus. They had lockdowns, military lockdowns. So they managed to control the epidemic. And so at the time, we wrote a paper, we communicated to them our results. They said, please keep it live because we want to know if there's going to be an outbreak. But it seems like we controlled it. And so us as scientists, we said, oh, well, let's use some of our, as I said, let's do some projections of what would have happened if these interventions hadn't been put in place. They still felt like we were doing work about something that happened some other part of the world that was not a threat to us. And so we showed that, in fact, these lockdowns that happened here, had they not been implemented, this is what we would have expected would have happened. And so we wrote this paper quantifying the number of deaths that would have occurred and so on. It's very scientific. But then this happened, and you may remember, right? So COVID leaked out of China, and then of course we started to witness outbreaks, and so I think it was about around this time, I was called by a former student of mine who was the liaison between Congress and the national labs in the U.S. And he said, do you think this is going to be a problem for the U.S.? So then, at the time, both Xi Jinping, the president of China, and former President Trump, they said, don't worry about it because we know that these outbreaks die in the summer, so it's likely that we will not even see them here. So we thought, okay, well, let's see what they're basing their understanding on. And so there's this curve that shows you that, do you guys know what the reproductive number is at this point in time? Have you? No. So in epidemiology, the reproductive number is the number of secondary cases from an index case. So if I'm sick right now, how many people on average will be infected by an individual who's sick, right? And then there's also a timing. How long will that take, right? So whenever the reproductive number is larger than 1, if I infect 1.1 on average, then from a differential equations perspective, you'll see that the derivative of infections will be positive, so it will go up, right? So it will be an outbreak. So this here, people have looked historically about influenza outbreaks, and they have established this relationship. It's an empirical relationship that when it's hotter and more humid, the transmission is lower, and when it's colder and drier, then transmission is much more prevalent. And so this is what they were using, both the president of China and our former president. So we decided to look into whether that was what we were seeing, because China is a huge country, and while this outbreak happened in December and in January, most of it, they had all the climates that mostly there in the planet in their territory. So we said, okay, whenever you see dark green, this is a place that's really warm and even and humid, right? And so the circles show you the size of the outbreaks, the number of people that got sick there. And the color tells you the reproductive number. So in principle, we were expecting to see in these very dry and cold places, we were expecting to see really really red colors. So that meaning that the outbreaks were really bad because according to our hypothesis, right, that's where outbreaks would have been the worst. And in these areas, we were thinking it's warmer and more humid, so we should expect to see, smaller reproductive numbers. And if I show you this, then right, you don't see any pattern like that. But we analyzed it from a statistical perspective, and so our conclusion was, no, it's just, it has no role in the speed of transmission. And so when I was asked to testify in mid-February, I said, yes, this is going to be a threat. And no, in the summer it's not going to get better, according to what we have seen. I mean, it may be that in other countries it will be different, but according to what we have seen, it's not going to be better. And so at the time, then we had all these data sources that I just told you about, and they said, well, can you produce an early warning system that tells us when the next outbreak is going to happen in the US? And so, this is for New York, but I have a very similar plot. It's available for Massachusetts, and Massachusetts at the time was dominated by Boston. So I think it was in March 12th when they asked me to testify in front of all the city mayors. Boston, it's called Boston like it was a single city, but it's actually multiple cities, like, I don't know, 30 or something like that. It's a cluster of cities. And so they each one have a mayor, and to your point, how is this being used? Well, each mayor has to be convinced that, what we're saying makes sense. And so what I'm showing you in this plot are snapshots in time of what we knew during COVID. In these 1, 2, 3, 4, 5 dates, March 1st, March 13th, 23rd, April 18th, and May 30th. And what I'm showing you at the very top are the signals that epidemiologists are normally looking at, which are how many cases am I seeing, how many people are dying, and one metric that we proposed at the time to look at is how many influenza-like illnesses there are that cannot be attributable to flu, because you test people, right? So in March 12th, they asked me to tell this group of people whether I thought things were getting bad in Boston. And we were seeing these signals, each individual signal that I mentioned to you before. We started seeing this exponential growth of people searching for symptoms for COVID, or how do I treat a sore throat? We also had signals from clinicians that were prescribing antiviral medicine that was not available for COVID, but people didn't know if it was COVID because the tests that we had were not very good at this time. And in fact, all these signals were flat here. Not so much here, but here definitely flat. And so, however, these other signals, all of them were going up through the roof. So we said, look, based on what we have seen in other countries, at the time, Italy and Iran had been devastated by COVID. We said, we think, because we don't have a treatment plan, we don't have a vaccine, we just don't know what to do with people. And people may survive if they receive some support. Then we should keep beds or occupancy as low as possible in hospitals. That means we should probably propose some kind of stay-at-home order, just what we figure out, what to do. So Boston was closed that night. They said, okay, we're going to close it. But then, 10 days later, I remember, and as I said, Massachusetts was very similar. They told me, we're still not seeing anything. And each day that the cities close costs I don't know how many hundreds of millions of dollars because economic activity is, it's blocked. And we don't really know, and you can see here that this is human mobility. This row is human mobility, so people were starting to not go to work. We said, well, this is what we're looking at in terms of our signals. So we do think that things are really, really bad. even though we're not seeing that in what people call the ground truth data. But then, so, a month later, this is what became apparent. So these signals, as you see, for us are thermometers, so they're signaling that things were starting to calm down. And this is what we were starting to see in the top signals. And so this was the first exercise in an emergency in the US that we had the opportunity to use our models. And let me see if I have. Yeah, so this is, so at the time then I proposed that to the CDC that what we should have is an early warning system that would be monitoring all these signals in every single city. And, for some time we did that, and, the equivalent of this, and I told you I had done work in intensive care unit, because when we have a patient that's very sick, we place them in a room like this to monitor all their vital signs. So I said, this is precise. So these are the vital signs signals that we have in our cities. So we should be monitoring them, and then making sure that the treatment or the way we are behaving is actually achieving what we want to achieve, say reducing deaths and so on. So I wanted to tell you more about some other aspects of uncertainty in epidemiology, but it's 11:50, so I'm going to stop here and I'm going to take questions.
Thank you.
Thank you.
Any questions?
Your ensemble model that's like a Frankenstein of everything,
Yeah.
is each model tracking a different input, a different thermometer,
Yes.
or are they
Yes.
tracking? Okay, so that's how they're stitched together, is they're tracking
Yes.
each input.
So each one of them is built to be a predictor with the limitations of the input information. And that's why it's a Frankenstein, and that's why we call them weak predictors,
Sure.
because we never know if we may see some gigantic bias emerging from them. Yeah.
How do you weight them?
Very good question. So we, one simple way to do it is to assess their accuracy in the past few weeks or months, and then have a a weighted average that favors the ones that have been better lately. Does that make sense? And that's because the relationship between the input variables, say the way in which people tweet, or the way in which the clinicians are searching for something that may be relevant, that may change over time. And in fact, we see that with Google searches. I have some slides in the talk where we can show that. But the bottom line is that people, not only because we change as people in the way we engage with we get better at searching information, but also the search engine changes. And Google, back in the days, you could mistype something and it would still give you an answer without auto-correcting you. Nowadays, for you, the new generation, all you see is you type something and it starts guessing, right? Or on Amazon, like it guesses, it has an autocomplete. And frequently offers something. So that changes the way it biases you to ask certain things that the system wants you to ask rather than what you wanted to ask. Does that make sense? That means that if you think of those signals as your input, you're perturbing your input signal. And so you need to reassess the relationship between your input and your output. Does that make sense? Yes, of course.
So for the last case that you showed me, COVID, that you were predicting it, but they're not seeing it in the hospital, but there seems to be a phase lag.
Yes.
Right? So is there like for future outbreaks of other things like or for different issues?
Yeah.
Is there a way to predict the phase lag or the lag you essentially end up seeing?
In a way, and yes, in fact, we quantify that. I have a slide for you, but the answer there is that here. So here, what we quantified is, so this is real time, and this is, for example, when let's focus on the uptrend. When that started to be going to ramping up, we saw that this all these signals started showing an uptrend, say up to like 30 days before. And that kind of tells you, so that number for future outbreaks will have to do with also some biology. Namely, if a person gets infected with a certain disease, they may die in 2 days, if they are going to die, right? Or they may survive and that's it. But for other diseases, it may take 10 or 30 days, depending on the age of the person, right? So there's some biological way to answer your question. And there's also the empirical way, which is this. So we just measured it and we just didn't know if this was biological or not, right? But then if you look at the cases, so you start seeing the shifts, the anticipation shrinks with respect to different signals. Does that make sense?
Yeah.
So, yeah.
I had a
Please.
more general question. So since you're a mathematician and work on different topics before you answer it, what are the other things that you think like predict models like these? Like similar issues like prediction
Yes.
of health, like
So
similar challenges like like CDC cannot enforce
of course,
things
of
that,
course.
Like, many of the federal regulations have the same issue.
Yeah. So many of my former students work in hedge funds, and so basically they are doing anomaly detection and establishing historical patterns between signals and how the price of a given stock or a given financial instrument may go up or down. So in terms of transferability of models or modeling frameworks, that's a big one. And so they think, oh, I can go to the CDC and predict outbreaks, and then, or I could go to, I don't know, Citadel or I don't know, like whatever hedge fund you choose, and make a ton of money. Okay, I'm just going to choose to make a lot of money. I should say that the majority of my students end up there, sadly. Not sadly. I mean, they're doing it. They're having fun and they're making a ton of money, making a lot more money than I'm making, even at this stage of my career. So, in their first job. So, but anyways, sorry. Did I answer your question?
So actually, this is a simple question. So we are working on developing some models for prediction of onset of dementia in patients and using some driving, like basic driving data.
Mm-hmm.
So we have sensors which are included in the cars and trying to track the pattern throughout the year, time series, and then trying to detect. Do you think these models, the ability models, can be?
Yeah, I think so. Yeah, yeah. So yes. So I'm going to tell you how I think they could be used, and because this is the framework in which we think of this. So you have a time series, say your driving data, whatever. So you have the number of times that the person hit the brakes in the last n minutes or whatever, right? So that is a signal, right? And so you have a lot of features. And then if you have the ground truth or the labeled data, right? Then what we do is we extract. In this work, we extract very few features, but in other work, in the intensive care unit, where you have like all these collection of time series, we extract a lot of patterns. So you could extract, for example, I don't know. So because we extract 1,600, and some of these patterns come from astronomy or hedge fund analysis or from seismology, and so we just extract them blindly. And then we do dimensionality reduction. We say, well, we have 1,600 features, but maybe they're redundant. So we do dimensionality reduction, then you end up with, say, 150. Then we apply our machine learning algorithm that, say, predicts the multiple classes of how advanced is dementia, or is it dementia?
Yeah, dementia, yeah.
Right. And so then we do regularization because we want to prefer models that have fewer input variables as predictors, and so we do the loop. We verify. We do some. Did that make sense?
Yeah.
So
we are still collecting data, so we are testing some models, but we'll take a look at that maybe.
yeah, and I can give you. So I have worked in intensive care unit that may be more relevant for that.
Okay.
Yeah. Yeah.
So do you start with clustering and and for instance, those off? Did you just correlations start there.
Right. So back in the days, Google had a tool where you would pass a time series and it would tell you which search terms had a very similar behavior over time. But they discontinued that. So then we do semantic analysis and clustering nowadays. Yeah. So we use LLMs, for example, to tell us which terms may be similar in terms of how people talk about things, and we use them. And yeah. So did that make sense?
With that, it's 12 o'clock, so we've got it short here.
Going on time.
Yeah. Thank you very much.
Thank you, Albert.